All right, so let's start by talking about limits. Okay, so let's start with the idea that with a limit, we don't care about the value of a as x approaches a. We don't care what the value of the function is so much as we care about what it's approaching. The value as x approaches a, or the value at a itself, might not even exist, but we still have a value as we approach this limit. So let's take a look at that. All right, so we have the limit as, oops, sorry. We have the limit as x approaches a from the left. Okay, and we know it's the left. This symbol down here where it has a with that negative, that is not an exponent. That tells us that we are approaching from the left. So we are going to find the limit as x approaches a from the left and see what it's trending toward. Again, we don't care the actual value at a, we care what it's trending toward. And again, we're going to do the same thing as x approaches a from the right. That's what the plus sign by the a means. Okay, so that tells us that we are approaching from the right. If we have a limit from the left and a limit from the right, and they are the same number, then the overall limit exists. So let's look at something. Here's an example. What is f of 3? Now think back to domain. Am I allowed to plug 3 in here? 3 minus 0. That would give me a 0 in my denominator. Not allowed. So I cannot plug 3 in because I would get a 0 in my denominator. But I can still find the limit as x approaches 3. And we're going to do that by putting this function in our calculator. So using your calculator, go to the button that says y equals, and you're going to enter it like this, parentheses, x squared minus 9, close your parentheses, hit the division symbol. So the division symbol looks like that, but it's actually going to put a bar in like that. Open parentheses, x minus 3. Now those parentheses are very important. You're going to put that in y equals. And what that's going to do for you is then you're going to be able to go to the second function. You're going to use the button that says second, and then you're going to hit the button that says graph. You'll notice above graph, it says table. And you should get a table of values. Now, if you have never used this before, let me turn mine on real quick. Table. Okay, so if you've never used it before, it probably in the x column says 0, 1, 2, 3, 4, 5, and the x's go up by 1. We are going to not want them to go up by whole numbers, so we're going to want to change that. So what I need you to do is go to the button that says, so again, you're going to use your second key, and you're going to go to the button, it says on the top of it, window, but up above it says table set. Okay, so when you hit your second key, it opens up the words up above. So second table set, and you should see a screen that looks like this. Table setup. Okay, it probably has a table start, change in table. We don't care too much about those. What we are looking at is independent, INDPNT. And there are two options on there, auto and ask, and dependent. And again, it has auto and ask. Right now, auto is probably selected for both of those. And what we want to do is make sure that ask is selected for my independent variable and auto is selected for my dependent variable. Okay, what that's going to do for you is allow you to put in your own X values. So we're going to be able to create a table of values that we want for this specific problem and for each specific problem. So in this case, we want to find numbers that are close to 3, and I'm going to do 2 different tables of value here. We want to approach from the left, so I want numbers smaller than 3. So maybe 2, sorry, I said 2 and I wrote 3. 2, 2.5, 2.9, 2.999. Okay, those are the kinds of values that we're going to put in that table. Okay, the second table, we're going to put values in that look like this. They have to be bigger than 3, so maybe 4, but then we want to get closer to 3, so 3.5, 3.1, 3.01, 3.0001. Okay, so you see how we're starting at a number smaller and getting closer to 3, and then starting on our other table with a number bigger and then coming back toward 3. So if you look in your calculator, sorry, I'm putting this in real quick so I can tell you what the table of values says. And we put in these numbers that we have in our first table. So we put in 2, we get 5. 2.5, we get 5.5. 2.9, we get 5.9. 2.999, we get 5.999. Okay, and you can see you might want to even put in more 9s after your 2. But what you should see is that as we approach from the left, we're trending toward 6. Okay, so that table tells me I'm trending toward 6. I'm getting closer and closer and closer to 6. Let's see what happens on the other side. So we started at 4, and I got 7. 3.5, and I get 6.5. 3.1, I get 6.1. 3.01, I get 6.01. 3.0001, and I get 6.0001. And again, you can keep putting numbers in. You could put in 3.00000001 and see what you trend toward. But it looks to me like we are trending toward 6. So the limit as x approaches a from the left was 6. And the limit as x approaches a from the right is 6. So my overall limit as x approaches a is 6. And again, you can see that they've given you tables here, so you can see that same thing that we just did. Okay, we can look at the same thing on a graph. Sorry, this is a different example, so we're going to ignore that graph because it doesn't go with our problem. Don't know how that got in there. All right, here is another example. And we have 2 things here. The limit as x approaches 3, and then the limit as x approaches 2. So let's start with the limit as x approaches 3. So in your y equals, I want you to write it just like this. So you're going to hit that y equals button. So, sorry, y equals Okay, so we're going to have y equals parentheses 1, close your parenthesis, hit that division symbol, which will give you the slash, open parentheses again, x minus 2, close your parentheses, and then plus 3. That's what's going to go in your y equals. And again, you want to use your table to find those values. Now, we just had our table, so let's see what that gives us. So when I have x, y, when I have 3.5, so when I have 3.5, I get 3.667. When I have 3.1, I get 3.991. When I get 3.01, I get 3.99. So it appears that we are trending limit as x approaches. Now this time we started bigger and went smaller, so we're coming at it from that side, is 4. Let's look at what happens on the other side. We have two point five, we got 5.1, sorry, 2.9. I went the wrong way. We got 4.11, 2.999, we get 4.001. So again, from this side, it looks like we are trending toward 4. So the limit as x approaches a from the left is also 4. So our overall limit for this one is 4. Let's look again at this same thing when we are approaching 2. So the limit as we approach 2. So I'm going to go ahead and erase these so that we have a place to write here. All right, so 2 new tables of values. There we go. So x, we want to approach 2. So let's say we start at 1.5, 1.9, 1.99, 1.999, and x and y, so 2.5, 2.1, 2.001, 2.00001. Okay, so let's say those are our values. Again, you can choose whatever values you want. You need to try to get really, really, really close to 2 without actually using the number 2. So looking at our table, we have 2.5 gave me 5, 2.1 gave me, gave me 13, 2.0001 gave me 1,003, 2.00001 gave me 1, 2, 3, 4, 5, 6. Okay, so the number just keeps getting bigger. That means we are trending toward infinity. Let's see what happens on the other side. So we have 1.5. We get 1.5 gave me 1. 1.9 gave me -7. 1.99 gave me negative 97. 1.999 gave me negative 997. Now let's suppose we did one more. We just put a whole bunch of nines in there. So 1.999999 gave me negative 99997. So this side is getting smaller and smaller, or bigger and bigger in the negative direction, however you want to say that. This one is going to negative infinity. Okay, so the limit as x approaches a from the left is negative infinity. The limit as x approaches a from the right is infinity. Now, since negative infinity and positive infinity are not the same thing, the overall limit as x approaches a does not exist. Okay, let's look at another example. We are going to use the same problem again. This time I want to find the limit as x approaches infinity. Okay, so what that means is I want to make x get really, really, really big. I'm still using the same formula. We should already have it in our y equals, but I want to make x get really big. Now, let's think about this. Can I ever get around x to the other side of that? I'm sorry, around infinity to the other side to come back toward it? No, so this is going to be a one-sided limit. So all we have to do is find the limit from the left. We can't get to the right side because we can't get bigger than infinity. That's just not possible. So when we do this, we're going to get a table of values, x, y, and just pick some numbers that you think are big. Maybe we start with 100, maybe we start with 1,000, 10,000, 1 million. And you just keep picking numbers until you see a pattern emerging. So let's go ahead and put those values in for x. So I have 1,000. And when I have 1,000, I get 3.001. When I put in 10,000, I get 3.0001. When I put in 1 million, I get 3.0000001. So it looks like the limit is trending toward 3. Again, I don't care what the number is when I'm actually at infinity, because I can't actually get to infinity, so that would be impossible to do. But I want to know what we're trending toward. And we can see the closer and closer and closer we get to infinity, meaning the larger x values we put in, we are trending toward 3. And here are the tables for that same thing. All right. Now, some properties of limits. The limit of a constant is the constant. So let's think about this. When we're talking about a constant function, we mean something like y equals 5. Okay. So we are talking about a line here, y equals 5. So no matter what x value I put in, I'm trending toward 5 because my line is always 5. So the limit of a constant is that constant because you can't get any other value out. So no matter what I put in for x, I'm going to get that y out. So that limit is going to be whatever that constant is. Okay, some of these limit properties you're going to use without even knowing you're using them. So the limit of a power function is the limit of the base raised to that power. So for example, if I'm taking the limit of some function raised to a power, what I can do is take the limit of the function, get the answer for the limit, and raise that limit to the power. Okay, and the same is true for radicals, because remember, radicals are just rational exponents, so they are still power functions. Right, this would be, if I rewrote that, that would be f of x to the 1 over n. Right, so radicals and powers are the same thing. We just rewrite them. All right, there's a couple other. The sum or difference. The limit of a sum or difference is the sum or difference of a limit. So if I am adding or subtracting two different functions and I want the limit, I can take the limit of the first one, the limit of the second one, and add those two limits together or subtract them, as the case may be. Same is true for the product. If I have two things, taking the limit of their product, I can take the limits separately and multiply those limits together. And the quotient, so a fraction of the limit of a quotient is the quotient of the limits, meaning if I have a fraction I'm trying to take the limit of, I can take the limit of the numerator and the limit of the denominator and divide those after I take the limits. Now remember that only works if m, my denominator, is not 0. And the final one is the limit of a constant times a function, of a constant times a function, is the constant times the limit. So I can pull this constant out in front here, take the limit of the function, and then multiply those two things together. Okay, again, these are just properties. You're probably not even going to realize that you're using them when you do, but we need to know that they exist. All right. So this one, we're going to use the sum and difference properties. We're also going to use a power property. We don't even realize we're doing that. So, excuse me. The limit of x squared is the limit of x, which is 4, times the limit of x, which is 4. So the limit of x squared is 16. That was the first term. The limit of negative 3x, well, we took the constant out in front, take the limit of x, well, that's going to be 4. So that's negative 12. And the limit of a constant, which is at the end, the limit of 7 is just 7. Okay, so you can see how we used a lot of those properties, but when we're doing this, you're not even going to realize that you're using those properties, but that's just kind of how they work. Okay. Theorem 2, limit of rational functions. So we've been using tables of values to find our limits. And that's great, and it always works. But for certain functions, if I have a rational function and a is in the domain, now remember we've had some where a wasn't in the domain, but if a is in the domain and it's a number that I can actually get, then I can plug it straight in. And whatever the answer is my limit. So when I have a function where I can plug a straight in and get a value, that will be my limit, is what this function says. So when we start these, what we're going to try to do is the first thing we're going to try to do is plug a in and see if that works. Okay, so let's look at this one. We have the limit as x approaches 0. Well, let's see if it works. 0 squared minus 3 times 0 plus 2. Okay, so 0 squared, well, that's 0. Minus 3 times 0, that's still 0. So when I simplify this, I have the square root of 2. So that is my limit. When I plugged 0 in, my answer was square root of 2. So that was the limit as x approaches 0. Okay, those are some other ones that you can practice if you want. Again, you should be able to plug in on all of those. I want to talk to you about this one, though. The limit as x approaches negative 3 of x squared minus 9 over x plus 3. Am I allowed to plug negative 3 in here? -3 plus 3, that's going to give me a 0 in the denominator, so I'm not allowed to do that. But let's see if there's something else we can do. If I have x squared minus 9, that factors. So that's going to equal x plus 3, x minus 3, and that's going to be over x plus 3. Okay, I have an x plus 3 on the top and an x plus 3 on the bottom, so I can simplify that fraction. And when I do, I have the limit as x approaches -3 of x minus 3. Can I plug -3 in here? It doesn't cause a 0 in the denominator. It's not going to cause a negative under a radical, so let's go ahead and do that. So we have -3 minus 3, which equals -6. So the limit as x approaches -3 is -6. Okay, and our last slide that we want to talk about is when a function is continuous. Okay, so there's a test for whether or not a function is continuous at a given point at the value a. Number one, we have to be able to get a value when we plug a in. So if we can't get a value, if we can't plug a in and get a value, then it's not continuous. Number two, we have to, the limit as x approaches a has to exist. And number three, the limit and the value when we plug a in need to be the same thing. Okay, so for it to be continuous at a specific point, I have to be able to plug a in and get a value. I have to be able to find the limit at that specific point, and the limit and the value when I evaluate the function have to be the same thing. Okay, and a function is continuous over a whole interval if it is continuous at each point, each a value within the interval. All right, so that is it for this lesson, and I will talk to you soon.